aim today is to state a property of residually finite groups, which says that if a finitely generated group has many images which are linear of the same dimension, then actually the group is residually linear, and then it has an infinite linear image, and also it has a lot of other finite images that come as congruent images of some simple algebraic group. But I thought before I do that, I'll just go back a little bit and give an illustration of the methods of algebraic groups to prove results about linear groups, and in particular we'll show a proof of the Lee-Cauchy theorem. So remember the notion of connectedness for algebraic groups, which was the same as being irreducible, and there is the following result. Theorem. Suppose that if G is algebraic group, and I have some collection of it's a family of closed connected subgroups. G, then the group that they generate is also closed and connected, and in fact is equal to a finite product of some of the HI with repetitions. So this is an application of, I mean, this is not an immediate result. I'm not going to prove it here. I'm just going to say a few words where it follows. The key to it is the notion of a constructible set. So it's not true that if you start to multiply these groups, you're going to get necessary closed subsets immediately. Yeah? The product of two algebraic groups may not be closed. But it is a homomorphic image of a closed set, and therefore there's a theorem by Chevalier which says that the image of a constructible set is constructible. So constructible sets, by definition, these are the sets which are the closure of open and closed sets in the Boolean algebra of the subsets of G. So you can show that a constructible set is basically a finite union of sets, each of them of which is dense in its closure, and using this you can prove this using also the notion of dimension, because you're going to argue. You're going to start multiply the ages, and you're looking at the dimension of the Zariski closure of the product at each stage. And then at some stage, this must, after a finite number of steps, this must stabilize. Okay? And then this means that with a few more steps, we have. I don't want to. Another same method.
So, Nicolay, the product is not a Cartesian product. I mean,
No, this is a product inside the group. Yeah, this is what they generate. Yeah.
It's boundedly generated by some.
Yeah, it's a bounded generation for for algebraic groups. We always have bounded generation.
it's a function.
For connected subgroups. And same method shows that the derived subgroup is so if if G is connected, then so is the derived subgroup. This is the group generated by all commutations. Okay, so now let's prove a theorem, the Lee-Cauchy theorem. Says that if now gamma is a solvable subgroup of G, L, and K, some field K, then gamma has a finite index subgroups, has a finite subgroup 1, which is triangulizable. Right? And well, wait. Over it's algebraic, so over some algebraic. Yeah, K is always algebraic. K is algebraic. If K is not algebraically closed, then passing to the algebraic closure, you can triangulate gamma 1 over the algebraic closure, but even without going to the algebraic closure, you know that this gamma 1 is solvable of length bounded by n. Yeah. Alright. And so we can replace, so in the proof we can replace gamma with its closure, Zariski closure. G. Now notice that even though I defined algebraic groups as closed subgroups of SLN, I can think of GLN as a closed subgroup of SLN plus 1. Okay. So I'm just thinking. Yes.
Can you explain the conclusion of the theorem? What is the learning to the theorem?
What is?
The last word in the thing.
Triangulizable.
What is it?
So there's a basis with respect to which gamma 1 is upper triangular matrices. Equivalently, gamma 1 preserves a flag, a complete flag. Okay, so we can replace gamma with closure, and then we can replace, then we can take the connected component, take G0, and put, and we will prove actually that we will show G0 connected component. And so we can assume, so let's assume from the start G is connected, and I will show that G is triangulizable. Triangulizable. So you actually will show that the connected component is triangulizable, and because it has finite index, this will intersect gamma in a finite index of gamma 1. Okay. Now we can do, so we prove the following statement by induction on the derived length. We prove that there exists a subspace, there exists a vector V, non-zero vector kn 0, which is such that the one-dimensional space KV is invariant and destabilized under the common eigenvalue. So this is the first statement we prove, which we're going to prove. This we prove by induction on the derived length. It's true for abelian groups. It's a well-known fact for abelian groups. True for G abelian. And now, going down to G prime, we can assume is therefore by induction on derived length. True for G prime. So there exists some eigenspace, right? But now consider all possible. Now, if I have an eigenspace, and then if I have an element G, and then this G maps on B is equal to some lambda V, and this is the eigenvalue of G. But then the map which sends G to lambda G is a character, right? So this is call this map F V. Is a map from G to the non-zero scalars. This is a character.
Wait, this isn't on G prime.
G prime, yeah. That's right. G prime. And then we can define for any character, for any f in home G prime C star, define the eigenspace which gives me this character. So let Vf be the set, yeah, okay, all those E in K M such that Gv is equal to F of G. Right? Then different characters give subspaces which are with the trivial intersection. It's an easy exercise. So F not equal to F prime means that Vf intersecting Vf prime. So, because the sum of these vector spaces is of these common eigenspaces is actually their direct sum. There are only finitely many of them. So they basically there exist some finitely many characters such that I have some composition. Let's say inside T and there are no others. But then the conjugation action, so if G now is in G, not in G prime, then G of V Fi is equal to Vfj, yeah, some J, right? Because this corresponds to the conjugation action of an easy exercise. Yeah, that's the action of the group for Nietzsche. Right? And this is an algebraic action. So this way, basically, G acts on home star. So this is an algebraic action with finite orbit. Right. So therefore. Therefore, it fixes some. So it fixes.
Why is it finite orbit?
Because if I take a direct, if you take the sum of several different linear functionals, of these eigenspaces, they generate the direct sum. So they can only be at most n. In fact, it's m, which is less. Okay, so so because G is connected, G does not have closed subgroups of finite index. It follows that G fixes some of them. So G fixes. Right? By fixes, I mean it leaves it invariant, right? So leaves it invariant, preserves. Okay. Now it can happen that this is already the same, the whole space, in which case we don't know anything yet, right? Looks like this could be the whole space K to the n, yeah? But it cannot happen because now a claim is that VFI cannot be equal to the whole K to the n. Because what it means in this case that that basically G prime acts as scalars on the whole space, yeah? It acts as the same, every element of G acts as the same lambda. So it acts as scalars. But it also acts as matrices of determinant 1. Because it's a derived subgroup. Yeah? But then the scalars of determinant 1 are just a finite group. So G prime cannot be a finite group because it's connected. Trivial. Yeah. So if okay. So this is a proper subspace. Right? And then we can continue by induction, right? So the moment now we have some subspace, and yeah, so then the rest is easy, yeah, because then I have some subspace V, which is preserved. So if I take a basis with respect to V, my G will look like upper triangular matrices, yeah, right? Right. And I'll just look at the action. Now look at the action here. This was a key point. Or another way, we prove that G is not irreducible. In that case, if it's reducible, then it can be by that. Right. Okay. So, sorry, it's too long.
Did you assume that you were on infinite field somehow?
Yeah. This is over the field of C. Right. So now I want to define. There's still a few definitions we need to do. I'm going to define semi-simple and simple and simply connected algebraic groups. So let's start with the Jordan decomposition. So if I have now G inside S, L, and K, algebraic, then I have the Jordan decomposition. Where each G in G can be written in a unique way as a semi-simple tying a unipotent element where GS is diagonizable, also called semi-simple, and GU is unipotent. Okay? And they commute. So we know from linear algebra that every matrix can be written in a unique way in this form, and the proof actually also shows that both the semi-simple and the unipotent part lie in G. Right? And actually, both GU and GS lie in G. Okay, it's true, but I don't think we don't need it. And now we say that the group G is unipotent if every element of G is unipotent. Okay. Now I can define G semi-simple. It's an if thing to say G is semi-simple if all the elements of G is semi-simple, but actually this just gives me a billion groups. So there's a good reason that you're not going to get anything. So, and that's not the meaning of semi-simple groups. And also, it's a fact that G has a largest normal unipotent closed subgroup. Sorry?
You assume characteristic 0?
Yes. In everything I assume that this is it's not necessarily everywhere, but I just if I assume finite, if I start to assume finite characteristics, then I have to think about counterexamples. So there's a largest normal unipotent closed subgroup. This is called the unipotent radical. Exercise proves that it's automatically connected. Okay. I didn't say connected here, I could have, but I didn't. Okay. And there's also the solvable radical. G has largest normal connected solvable subgroup. Denoted the radical. Okay. So the proof now, from what we know, is easy because we can just take the one at largest dimension. So if you certainly there's a bound on the dimension of the subgroups of G, so take the solvable connected normal subgroup of largest dimension, and I claim it contains everything, because if there were two of them, I take the product. Now this is a subgroup because they're both normal. So this is a subgroup. This is a subgroup, and it's constructible, which is automatically connected, and it's normal because product of two are normal. It's normal, and it's solvable because product of two solvable normal. Yeah. So yeah. This false. And now a G is called semi-simple if it has trivial radical. G is called reductive if it has no unipotent normal subgroups. So clearly, semi-simple implies reductive, but not conversely, because a torus, a diagonal subgroup is reductive but not semi-simple. Yeah. So if I put T with the matrix. This is just basically the direct product of the field. Then this is it has no unipotent elements, so it's reductive. but it's abelian, so it's only, this is a connected group, so the T is connected, and the radical of it is everything, so it's T, so it's not semi-simple. Right, so there's a useful result here that says that if G is reductive, theorem, if G is reductive, then actually G is a product of then G is equal to T when connected. So such that G is a product of TS, where S is semi-simple, and T is a B. Diagonal. And this product is also TS is equal to T and S commute. In particular, this means that the intersection of them is finite. T intersecting S is inside the center of G, which is inside the center of S. But the center of S must be finite because the radical is 1, so it's not connected. All the normal subgroups must all the normal abelian subgroups must be finite. Which is fine. This we denote.
So the center of G is not contained in the center.
Under this situation, oh no. Sorry, yes. It's T. But certainly in the center of S. T is in, you know this situation. So this is the notion of a central product of groups. So we denote T circle S to mean that the, T and S are normal groups which commute between themselves, and the product and the intersection is finite. Right. And of course, now we can define, and I'll call it torus. So this is called torus, yeah. And this is basically torus. Now, G is simple. Basically, if G has no connected normal subgroups, so I take G. This is a definition. And In this situation, so it's actually this is usually called absolutely simple.
We're working over closed, algebraically closed field, or
Yes, my K is absolutely and now let's discuss a little bit about semi-simple groups. So a semi-simple group is basically almost a product of simple groups. So if G is semi-simple, then basically G is isomorphic over K as with a central product of some n central product simple groups. Again, this means that each of these groups commutes with all the others, and the product each. But it's not necessarily the direct product. Now,
And the intersection is finite?
yes, the intersection of each pair of them is finite. This is because the center, the intersection of each pair of them is the, if we take SI intersection SJ, this actually is inside, now this commutes with the other, right? And this is inside and it's also inside, I really want to say. So now what about simple groups over algebraically closed groups? So at this moment I'm still making this assumption. Can we classify simple groups? And the answer is yes. So here's a classification. If G is simple, then there is a special. There is a special, and the technical name is simply connected. This is a new, simply connected simple algebraic group. G tilde and a homomorphism of algebraic groups. Subjective homomorphism with finite groups. Notice that actually every normal subgroup of a simple group must be finite, and because the group is assumed connected, it must be actually central, because the conjugation action, otherwise you have an algebraic action on a finite set, so the stabilizer point will be a finite index closed subgroup, which is not allowed. So because this is a finite, finite subgroup, it must be in the center of G, which is fine.
So when
Now-
you say simply connected, you mean in which topology? When you say it is simply connected group, G tilde. So in which
So the
topology?
meaning of simply connected is motivated by the Lie algebras with the Lie groups, where this is indeed a simple. In the case of Lie groups, this G tilde will be simply
So
connected.
does it mean here? What is the definition here?
Sometimes it's called universal instead of this. universal. So okay, so what it means? So the meaning of this is that I have to tell you a little bit more about these, but there's a Dinkin diagram and a lattice of weights and co-characters, and being simply connected means that the one lattice is equal to another lattice.
But it's equivalent to the C point is, right?
Manifestation K is C.
Yeah, this is the case. So I was about to say here, the isomorphism classes, K isomorphism classes of these universal groups are in one-to-one correspondence with basically simple Lie algebras. Okay, so this is basically parameterized by Dinkin diagrams. So for each Lie type, which is a Dinkin diagram, there's up to an isomorphism over the algebraic closed field. There's just one universal simply connected group. So, e.g., if the type is an minus 1, then G tilde is SRN. If type is Cn, then G tilde is symplectic group, 2n, and also G tilde could be one of the covers, the spin cover of the orthogonal groups. This is in type Bn, Tn. So, okay, this is not the same. This integer is about half of this one. You never know. So these are the classical simple algebraic simple groups, and also they're the exceptional ones, yeah, the E's and the yeah. 7, 8, G2, F4. Right. Now, let's return here, and I'm going to need this later, so let's pay attention here. Even though this is a surjection on the level of the algebraic closure of the field, often we want to take rational points. So, so these groups are often defined over a subfield. In fact, the canonical definition of them is they're in fact these ones are just defined over Q. Yeah. So this makes sense to so assuming now so now L is a subfield. And this is assuming that G and G tilde are L defined. I can consider the points of the L points of G, and then of course I have a map from the L points of G tilde, and this is called an isogeny. Such a morphism of algebraic groups with finite kernel and surjective is called an isogeny, and it's also assuming it's defined over L. Then I have a well-defined homomorphism between these algebraic groups, but in general this is not surjective. Okay. And the best example is probably here. If here I take G to be a PGL, N, So SLN maps onto PGLN. Yeah. But then if I look over a finite field, say, not finite. Okay. Suppose I look over the rationals, and then I'm talking about a map which sends SLNQ to PGL and Q. And this is not surjective, right? Here I have a determinant. There's a bit of the determinant remaining here. Not surjective. Syntax. Actually, it's an infinite index, right? Q.
You can sort of Q over Q star.
Yeah, this is Q star, yeah, Q star. I mean Q star. The multiplicative group of the rationals is free based on the primes. Yeah, and then if you take the n powers, each prime you get the index n. So it's not a big. But in all cases, so here is a proposition that G of L modulo the image of G tilde of L is always abelian of exponent dividing the exponent of the set. So this is a finite abelian group, which is actually very small, usually just of size 2 or 4. Except in type G before. No, in Dn, but maybe G2. Ah, yes, An, yes, of course. Yes. An is exactly the same. So this is just there's a way to reduce this using Galois homology and so on, but it's much simpler because if we look at the point here, so we look at some G in G of L, so and then it is the primit of something, so there exists some G tilde in G tilde, such that f of G tilde is equal to G, but this is now so the surjection happened over the algebraic Gauss field, so there exists a preimage which is over the algebraic Gauss field. And then what does it mean that this is in GL? This means that for any automorphism alpha in the Galois group of K over L, G alpha is equal to G. But if you see what happens here, alpha is alpha is compatible with F because F is assumed to be defined over L. So this is F of G tilde into alpha, and this means that this is congruent to G tilde, not the center of G, because the kernel of F is inside the center of G. Okay. Ah, sorry. No, this is equal to G, therefore, which is equal to F of G tilde, therefore, G tilde alpha is congruent to G tilde, then G. But then if I take two of them, then if I take G1,
Center of G tilde. The center of G tilde.
center of, yeah,
No, no, here's G. And the first one is G and the
Just
second
G
one
without
is
mod anything. No,
here, yeah, I see. So now this is the module of theta. But then if I take two of them and I take their commutator, because each of them differs from the original G tilde by a central element, and central elements disappear in commutators, this is just the commutator of just G1 and G2. Okay. So basically, each commutator is inside the G tilde of L. Right? So this shows that it's a billion because the commutator of any two elements lies here in the. I mean, this is F of. So this is F of. Because F is a homomorphism. F of this. So if I take two elements in GFL, the commutator is in the F of the rational image of the rational points of it's in the image of the rational points of the universe. Yeah, so this shows the billion, and for the exponent then you just instead of taking a commutator with two elements, you just raise one of them to the power of the set. Right. And now I want to explain. So this was the absolute case. Yeah, this is when we classified simple. Well, we didn't classify, but we stated the classification over the algebraic closed field. In which case, it's relatively easy. Basically, it mimics the classification of the algebras. Because maybe I should say a few words how this is proved. You kind of certainly your simple group G acts on its Lie algebra, and then the kernel is actually in the center, right? So the kernel is G. So you start to find here in the Lie algebra you have root subgroups. You have roots, and then corresponding to that you look for root subgroups in G, and you start to find copies of SO2. It's in Humphrey's book on linear algebraic groups. One chapter. Yeah, I noticed that because of this classification, a simple group always has unipotent elements, right? So it's because it contains a copy of SO2. Each simple algebraic group contains a copy of SO2, so it has unipotent elements. But the situation could be very different when we consider now a small field. It's a subfield. Ideally, I'm thinking of this as probably as an extension of the rationals, very small field. And now we say that the G is L simple if well, the same definition, but instead of if G has no proper connected normal L defined so now we only we are restricting the existence of L defined normal connected subgroups. Okay. Now, what can we deduce from here? Now, so suppose that G is L simple. Suppose. Then the first thing is to deduce that G is semi-simple. This is because the radical of G is L-defined. This is because it's a characteristic subgroup. So if I act by an automorphism fixing L, I fix the radical, but that I have a criterion which says that this is sufficient condition, in fact, sufficient and necessary condition to say that the radical is L-defined. If it's fixed under every go out and fix it. That's characteristic. But therefore, it must be 1. So I want also non-negative. Let's throw in connected. So G is semi-simple. Lucky for us, being L semi-simple and absolutely semi-simple is the same, because the radical is always defined over any field that we take. So being semi-simple does not really matter much over what field we talk. Alright. So, therefore, okay, so assume that, suppose L is simple and assume now G is universal. Assume G is simply connected. For simply connected semi-simple group, this just means its factors are simply connected. And the group is a direct product of the simply. Well, this means that G is a direct product of G1 times G2 times Gn, where each Gn is k-simple, or absolutely simple, and this isomorphism is actually k-defined. So this, if you now step back and think of G as a group of the algebraic closed field, then because it's semi-simple, it's a product and it's universal, it's a product of product of its simple factors, right? Okay, but then if I take any element alpha in the Galois group fixing L, then because G is the same as G alpha, after all G is L defined, these factors are unique after reordering. So I deduce that alpha permutes some of these factors. Yeah? So alpha permutes the factor G1, G2, and among themselves. Right? So take the first one, say G1, and look at its stabilizer. So look at the stabilizer in this action of G1. So this will be a finite index subgroup in this Galois group. Well, that to correspond by the Galois correspondence to a finite subfield. So this will be the Galois group of K over some L1, where basically the degree of the extension is exactly the number of factors. Not necessarily a normal extension, yeah? This does not have to be a splitting. And then taking, right, and then obviously, you see by definition, this G1 is invariant under all the elements here, right? It's invariant for all beta x in K over L1. So actually G1 is actually defined over L1. So even though this is an absolutely simple group, it is defined over finite extension of my field L. And then this should be remind you of something. It reminds you of restriction of scalars, I hope. It turns out that now G is so now G is isomorphic to the restriction of scalars of L. So maybe I should give you an example of restriction of scalars for this particular group, just to should I give an example? Okay. Let's just say suppose that L is Q, L1 is Qi, and I have the restriction of scalars of L1 over Q. So this I can represent as matrices A, B minus B, A. Right. So the way it works is we just act on the vector space of L1 as a vector space over L. So this corresponds to the scalar A plus IB, A plus IB, inside where these A and B are rational. And if I call this matrix CAB, C for complex number, I can define now the restriction of scalars of Qi over Q of G of the group S of 2. This is the smallest non-trivial restriction of scalars, of which gives me a simple semi-simple group. So this will think of it as a 4x4 matrices, right? Where we do put here C A1 A2, so A1 B1, C A2 B2, C A3 B3, C A4 B4. So this is a 4x4 matrices where we put these blocks around, and we want to put the condition the determinant is 1. So the condition is simply that, right, that this times this A1 plus I B1 times 4 minus the others. So we should think of this as a condition. This I here is just a dummy variable these are actually two equations. One is that the real part of this complex number is 0, and the other one is 1, and the other one is 0. Okay. And under this homomorphism, we see that over Qi, so if I call this group H, right? H is defined over Q. Yeah, all the equations here are with rational coefficients, but over Qi, H is isomorphic to SL2 times SL2. Right? Where the isomorphism simply sends this Ci, so this isomorphism is induced by this mark. And we also have a correspondence of the rational points. The rational points of H are isomorphic as a group to the rational points of SL2, but with coefficients in L1. And so the same thing happens with the integral points. Yeah? So that's basically the example which illustrates what happens in the restriction of scalars. We realize the rational and integral points of a group which is defined over bigger field as the integral and the ordinary integers and ordinary rational points of a group defined over Q. And notice that this is my example of a group. Now H is Q simple because H is Q simple because none of these factors is defined over Q because the complex conjugation swaps them. Right? The complex conjugation swaps these two factors, so they're not defined over Q. And these are the only normal subgroups. So H is Q simple, but it's not K simple, so it's not Qi simple. Okay. So now we have all the. When did I start?
About an hour ago.
Okay, let me just state the result that I want to sketch next time, and that will connect also with the end of my last talk. This is what I want to prove now. Suppose, so it's a combination of linearity criteria and Lubotsky's alternative. Suppose gamma is a finitely generated group whose finite images contain SLN pi for infinitely many primes. Yeah? And n is fixed, yeah? So n is some integer. Suppose that infinitely many SLN over pi's appear as the finite images among the finite images of gamma. And then the claim is that gamma has actually a lot more other images. Then gamma has a finite index subgroup gamma 1 and there's a Q simple simply connected algebraic group G. When I say Q simple, I also assume it's defined over Q and a finite set of primes S inside prime integers, such that delta maps onto all finite congruous images of the congruence completion G Z gamma. Yeah, gamma 1. So this is basically the product over all primes not in S of all periodic points of G at these periodic points. Notice that because G is defined over Q, even though in the definition maybe some of the equations have denominators, there are only finitely many of them, so I can take a finite set of primes avoiding the denominators in the definition, so this makes sense. Like it's okay to take the. So this basically will use. I'll start proving this next time. So we're going to use linearity criteria to prove that the group has a large linear quotient, and then restriction specializations to get it into a linear group over a number field, and then no revised by the theorem to get the last part.